great to see everybody here after 2 years of lockdown and COVID. And it's nice to be able to get to see old friends and colleagues again.
Doesn't it?
If we all jump to the lifeboats, is that okay?
So, firstly,
We are working our way.
That's another sort of energy sustainable technology that sort of is great but works against us. It also burns the grass in my yard.
Well, great conference. I'm hoping with that little that I live up to the morning standard of the speakers throughout the day, and it's been a great conference. And really appreciate the fact that we've had an opportunity to sort of bring in a lot of ideas, and hopefully I can touch on some of those as we go along. And so part of what I'm going to give you is a model, a new model, if you will, and one of the models that I had, and I was the project manager for a $1.2 million fire dynamics program for the Canadian Fire Service, develop a fire dynamics program for the Canadian Fire Service. 11 NATO countries joined, as well as Australia and Sweden joined this project. And it was known as Knowledge to Practice. It was a Defense Research Development Canada program. And in that program, we really wanted to take, and we're seeing that today, is people taking knowledge and putting it into practice. And so from the firefighters' perspective, that's what we need. We need practice in that information, okay? And this concept, a model that we took, and which is very evident in this conference, is we wanted to change what the word firefighter meant, and F was for firefighting, and firefighting was anticipate, prevent, intervene, and recover, all aspects of firefighting. I for instruction, whether that was children in schools, right through to, if you will, the graduate levels. R for research in all areas that are associated with these aspects of fire, and E for engineering, solutions to our problems. And so that was the ethos that we brought into, if you will, our model and our project. And that little Latin phrase doesn't say 2 hamburgers and a Coke. It says seek knowledge in fire, in terms of a Latin expression. Centerium quiere in ignia. So I'll start with a question. Where does the sun rise? Anybody? East. And where does it set? On this side? Where? In the west. That's not true. It hasn't been true since the 15th century, since Copernicus explained that, all the planets and the sun didn't revolve around the earth. Yet here you are telling me in the 21st century, heading into the 22nd, if you will, that it rises in the east and sets in the west. How is that possible? Doesn't make sense. Well, it's useful. It's a model. In fact, even though it is no longer true, we do see the sun track in this way, and we can use that to navigate. We can tell a lot of information, time of day. So there's a bunch of things that we use, even though it's wrong as a model, it's useful. And so there's a very interesting guy, George Box. He was a statistician, a British statistician, and he questioned the whole idea of models. Engineers might see them as limit states, the degree of sophistication of the model, that kind of stuff. So when we look at models, and Box did, and he said that the most important things about models is understanding at what point does the model, being wrong, cease to be useful, right? So that's the idea here. And so I'm going to give you a model. I gave you a fire model, and another model we developed as part of this fire dynamics program over time is a way to assess fire. And, firefighters use visualization on a regular basis. We want to know what's going on inside that box. And so from that, just looking at that simple picture, a skilled firefighter is going to tell you, well, that's a warehouse. You know, there's a lot of fuel in that warehouse. There's a whole bunch of information. It's banked down really low. It's ventilation controlled. There's a whole bunch of information associated with that fire, right? Well, we wanted to, if you will, build a model that could teach people sequentially. And again, at the end of the day, when you get on the fire ground, we're not going to use the model, right? It's a model. We need to make the decisions associated with what we see. And so that's the purpose of that model. And I guess the best way to describe models for you, it'd be do you guys know how to tie your shoes?
Yep.
100%. Could you tell me how to tie my shoes?
I can't remember.
No. So you see what I'm saying about the model. It's useful. It has its practical aspects. But at the end of the day, you're not going to actually go back and go, VP is equal to B safe, right? So it has its place. Now, the safe concept, smoke, air, heat, flame, a guy by the name of Shan Raphael, he came up with this taxonomy, right? Well, smoke, air, heat, and flame. Brilliant idea. Great taxonomy. Because historically, the fire service, when you ask them what's the signs of flashover, they would say, rolling fire, high heat. Basically, there was no taxonomy to the information. I might ask what? They would get it right. They had the information, but there was no taxonomy. So it made it sometimes difficult to teach or maybe to remember. Okay? So Shan came up with this idea, and we've used it and integrated it into what I refer to as the ventilation profile, what we see on the exterior of a building, and it's equated to the building and environmental factors. And so the whole intent here is to use this as part of your firefighter size up and for strategic and tactical decision making. Okay? And that's basically, I'm going to review parts of that. I'm not going to give you the whole model. There isn't enough time today. But the information, I'll show you where you can get all of it. Right? So the ventilation profile is a term I developed back in 2008. And I heard the good doctor here, Reich, speak to the issue of ventilation profile. I disagree with his definition. In fact, it's the issue of ventilation, the terms that we use, we talk ventilation profile, ventilation state, underventilated. There's a whole bunch of terms associated with ventilation. And so we looked at that in this program and said, you know what? This is what ventilation profile means. And that's been adopted by the National Fire Protection Association from our program. I was on the 1700 technical committee for the guidance for structural firefighting. And that guide is based on science, basically looking at fire dynamics and trying to bring that into the fire service in a meaningful way. So what I want you to understand is we're talking about the whole building. Air moving in and out. The doors are open. Someone opens that. We just changed the ventilation profile in this room. Okay? And that's the concept. And it's understood in the, Gerard mentioned pistoning effect. Others have mentioned it. Just understanding how that air is flowing, as the good doctor mentioned a moment ago, understanding all the possibilities as a firefighter is part of your understanding of what you're seeing on the exterior of the building as you pull up, okay? Or within the building. And now, I'm not going to give you a building construction course, but essentially, we teach in North America, and certainly in the Ottawa Fire Service extensively, we teach the factors, if you will, building factors that, if you will, lead to collapse. And understand the types of buildings, because we classify buildings by type, and those types being the NFPA types. And for those of you not familiar with them, and you may use the same here, it's fire-resistant, non-combustible, ordinary, heavy timber, wood frame, and PBD, which is performance-based design, which is, all bets are off. That is a wooden elevator shaft being tested in Ottawa at the National Research Council. It could be a stair shaft. We're building wooden high-rises, that kind of stuff. And looking at math versus math. So we explain those concepts to our firefighters as part of this model. Right? That jumped ahead. So occupancy as well as part of this building factors. Compartmentation, not only the cladding of the building envelope, but the interior, if you will, finishes, as well as the compartment size. These are all important factors to consider when we're evaluating what we're seeing. Openings, and there are a lot of openings in buildings, some designed, some undesigned. And occupant behavior also figures into the whole idea of what building factors, leaving doors open. We've heard, from a number of people here speaking as to the issue of how smoke is let to transit through buildings. And for understanding, it's not uncommon to have buildings that are, universally heated from one source in Canada, United States, I'm sure here as well, wherein effectively what happens is it's a nice day, but they can't turn the heating down, so they open all the windows. And so you have a whole different profile available to feed a fire. Okay? So, and then when we talk about fuels, again, these are building factors. Their state. What state are the fuels are within this structure? Flashover is a benchmark. Well, flashover as a benchmark of what? Well, that for us is there's sufficient energy in a flashover to degrade the protective finishes, and that may start attacking the structure. So it goes back to those building factors. It's evaluating where that structure is going to allow me to fight the fire over time. Rated assemblies, stopping, if you will, as well, and an active system such as sprinklers. So these are all elements that we evaluate. Now into the environmental factors, the flag, question the flag, right? That's the key, is what's going on. And the flag isn't the only aspect of evaluating for wind. You can listen at the doorways, see if there's a draft as you're opening buildings. There's a whole bunch of things that you can do. Again, I don't have time to go into depth on them, but there are internal and external things you can do, figuring out that wind. And of course, wind speed and direction creates a whole bunch of problems, right? It will accelerate fire growth, unlimited oxygen. And of course, the whole idea of forced convection, if you will, heat, no firefighter's PPE has ever been tested for convective heat transfer. It's all about radiative heat transfer. So we're not even close to being able to manage this with the PPE we have, okay? So that's a really important aspect of that. And of course, that drives all that smoke, air, heat, and flame. Okay? Now, Gerard talked about, that bushfires. Well, temperature and humidity has a huge impact if we're talking green walls and so on and so forth. And normally we would talk about this issue in the wildland setting, but we're not going to be talking about it in the high-rise setting, right? Because we've got these green walls. And if you can imagine this 14-story building, right, in Copenhagen, that issue is going to be, and it is an issue, especially with that wood backing all around it. And there's the front and the back of the place, okay? Just so you have an understanding. But that also drives stack effect. So not only are we dealing with the fuel issue on the exterior of the building, we're now dealing with, that whole issue of stack. And of course, that drives buoyancy, and if you will, the inside-outs air temperature driving that, if you will, and that temperature and humidity we spoke to, and the resulting differential pressures, okay? And you can see in this graphic, this picture that I took just before I got here, actually, is essentially a tremendous change, if you will, in the behavior of airflow within that structure, okay? So that chimney effect, and it results in building leakage. And that building leakage goes through a number of areas within the structure, and easily illustrated by a simple diagram. This is something firefighters deal with all the time in residential structures. Where's that going and how's it moving? That becomes much more complex in a high-rise, right? So when we look at stack effect, that significant stack effect almost the same forces or better in some cases, if you will, for forced combustion of the wind. So, and it has led to fatalities. Okay.
Tall Building Fire Safety Network delivers high-quality safety management training for anyone involved in the fire risk management of high-rise or tall buildings. Recognised by the Institution of Fire Engineers, we've been delivering fire safety training since 2011, and many organisations rely on our training for gaining competence in this field. Sign up for our training courses and conferences in 2023.
And I don't know about here, but in my jurisdiction, reverse stack. I know Ottawa, everybody thinks we have igloos. We live in igloos. No, just kidding. But it's very cold in the winter and it's very warm in the summer. And so that whole idea of, and in my career, I only saw reverse stack once, okay? Where a fire on like 7th floor, it just spilled into the lobby, okay? And so you don't know where the fire is. Right? It's not giving you the right cues, if you will. And we regularly use winter stack effect to our advantage to clear stairwells. Okay. So again, knowing that those large pressure differentials are quite available to us, and again, that serious injury and death, there are a number of fires throughout the world that have resulted from failure to manage that flow path. Okay. And weather in our jurisdiction changes what we see in terms of the visible conditions, right? Less buoyancy, the color, if you will, of the smoke changes because of the environment. It drops out the heavier particulate, or you may just see water vapor coming up through it. So essentially the characteristics of what I'm seeing changes, and that's going to be really important when we're looking at the ventilation profile, is understanding what impact the environment is having on what you're seeing. And I'll give you an example, very simply, is a basement, 1 floor below, storage lockers, and it's got to travel a significant distance. And essentially what we saw at the opening is not the raging fire that's inside. And so that's the issue associated with that. And of course, inversion layer, it gets very cold, as I said, so you can just have your smoke stay right on the ground. Okay, so that's not something that is uncommon in my jurisdiction. So that takes me to topography. So we talked about that green space from the concept of, if you will, those fuels, but it's also an associated issue with topography. And when we talk about topography, the shape of the land or the buildings surrounding, and when we look at those buildings, they all have an impact on how the wind will impact the structure, right? The aerodynamic effects associated with other buildings beside the building that is on fire. Okay. And you can see a little close-up of that 14-story nightmare. Did I say that out loud, nightmare? Yeah. And when I saw this building, I had a heart attack. And so, yeah, so you can see the fuel, and it's all wood back to it. It's amazing, right? And the hotel, well, Catherine and I were in Copenhagen doing presentations, and we stayed in this hotel, and you notice the signs. There were these signs all around the building because of the shape of the building. So it's not only the shape of the land, it's the shape of the buildings, right? And this building, by virtue of its weird shape, induces, if you will, tremendous airflow around its base. That makes it unsafe to walk, and they have to put signs that say, hey, look out, it's dangerous here. Think about that. And of course, building shape, as we just said, could be generate a lot of different effects. And those effects associated are related to the variations in the elevations of the land and or the buildings that we've just looked at, building geometry, if you will. So those aerodynamic effects, typically might be looked at in things like, I don't know, aircraft. Yeah, I got a pressure zone here, I got buffeting on the wing, all those things, but they're occurring in a rigid structure that now, if the windows are open or a flow path is created, creates very unique conditions, visualizations, ventilation profile ways. So understanding that, like this picture right here is the 4th Street Mall in Calgary. Without those structures that look like funny sort of flowers turned inside out, you could not walk on the 4th Street Mall during a Chinook. It would blow you down that concrete canyon. Okay, so that's actually for people protection, so they can physically walk down that thing and not be injured. Okay, and then of course, you know, if you look at how the air moves around buildings, and we do understand that, and this is not an uncommon occurrence in my jurisdiction, where you know the false hair comes right off the roof, right? It makes you understand, and we use it to illustrate the forces that are available to completely rip off a roof, off the finishes off that. So those are the pressure differences that can be just by the shape of the building and the way the air flows over it. Okay. So when we look at that Be Safe, we went through, you know, the ventilation profile, the building and environment elements, smoke, air, heat, and flame. They're indicators. They're like the dashboard on your car. You know, when you drive, engine oil, speed, temperature, all those things. That's basically what the concept of the smoke, air, heat, and flame. You can assess them individually. They can give you a lot of information, but you don't focus on one thing when you're driving, right? And you want to look at the building and the environment, you know, in that context, and use it to establish the ventilation profile, because that is where we want to be. We want to know what that's telling us. Okay. So the whole idea of smoke movement and control is one of the big aspects that we've talked about. Dr. Reich here gave us hey, we want to take care of that. And we know how it's being driven through the structure. And we need to manage those effects. So when we wanted to evaluate smoke, we can look at its volume, its velocity, and that's driven by temperature, its containment, how fast it's expanding, relative buoyancy. And you can get a really small space, but have a really high temperature, and it can push a lot of smoke. And you're thinking you got a monster. So you got to look at that in the context. That's why I say we got to look at it in the context of the structure. The density, in terms of its optical density, color, and we can tell things about, if you will, the quality of the burning process by its color. Odd colors is the general rule in the fire services called sneakers and binoculars. You know, you got to be far enough away from it if it's green. You know what I mean? If you got green smoke or pink smoke coming up, that's not good, right? So you get the idea. So there's things you can discern, but the key thing is to look for changes. And then we move on to air. And when we talk about air, well, we can't see air, right? So what we do is, contrast it with smoke. And it is the single most important factor in fire growth and decay. But when we put those two things together, we end up with the smoke-air flow. And that layering function that we typically see, the smoke moving out, air coming in, is read together to quickly establish those three elements of the burning regime, the flow paths, as well as the ventilation profile, if you're looking at the whole show. Or typically what firefighters do is we look at that main compartment. We might see one or two windows or just one window, the vent profile, okay? Now it's important to understand, we talked about models earlier, it's important to understand that our understanding of flashover and the rules, if you will, about flashover originate in the laboratory. It has a standard size opening, a standard area, and it has a bidirectional flow, okay? You got air moving in, fire coming out. So that's the model, okay? So when we talk about that, and it's a function of that gravity current, and that's just the density and the respective density of the air as smoke mass. And you got to understand that that can be disrupted by the wind or the combustion cycle. Because again, we've been built to model. Remember, I was taught the signs and symptoms of flashover. I don't know, symptom? What's a symptom of flashover? I got burned. No, you know what I mean? The fact is that there was language used that because we really didn't understand it, right? It wasn't the people teaching us. And we got to understand that the general rule is, on average, it takes 30 years to get a Nobel Prize. And why does it take 30 years to get a Nobel Prize? Because it takes about 30 years for people to universally accept the information that was developed at that point in time, right? And so if you think about, they developed as a science, fire dynamics, if you will, in the 50s. Come the 80s, when I joined, they still hadn't figured it out, right? And so we were getting the information from the 50s and the 80s. And, here I am in the 90s, and I'm going, how come you're still teaching them this stuff in the 50s? So, that's the progression of the fire service in a lot of ways. It's advanced immensely than that. But a lot of our information about how fire behaved really came from a laboratory, not real scale, full scale stuff, other than maybe experiential stuff, right? So when we talk about the burning regime, and historically, the whole idea of fuel controlled and ventilation controlled, and that took us a long time to figure that one out, right? It really did. And it was a concept, because our buildings changed. They became more sealed and so on and so forth. It took us a while to get that one straight. And that concept, again, it's a regime. And we like, simple answers. It's either fuel controlled or it's ventilation controlled. Well, the reality is fires are somewhere in here. They're all over that map, right? And so knowing that and understanding where you are in the regime, its potential, is the idea of our flow path. Because again, looking at smoke air, and again, another definition that I wrote that basically became the definition adopted by NFPA in the 1700. And this is important because in some of the previous literature, they talk about a bidirectional flow path. It doesn't exist. A unidirectional flow path doesn't exist. Okay, what exists is the flow path and then the flow within the path. The path is not bidirectional, right? It's just a single route, and those flows move within that route. That's critical to understanding. And it's important to understand the flow characteristics, and they include that stratification that they taught us in the flashover model, right? As well as understanding the turbulence, its direction, its velocity, and shape. Shape is not something we talked a lot about, okay? And those characteristics are best identified by looking at that smoke air flow. So I'll go back to firefighter modeling 101. This is the one we got. The figures courtesy of NFPA, 1700. So if I asked the firefighter, gave him the pencil and said, okay, show me fire 1, yeah, they'd mark it on the graph, they'd understand that. Fire 2, it would go on the graph, that's where it would be. Fire 3, boom. We would have no problem with that. It's a model we know and understand and have been taught. Like I say, we had some trouble with that dotted line for a while, but I think we got that worked out and understand the potential, the energy release that's available when you get to number 4, okay? And that concept was something that, took us a while, okay? So when we look at the types of flows that are available, and they be classified as unidirectional flow, a bidirectional flow, and a dynamic flow, okay? So this again was introduced via FKTB, from knowledge to practice, into the standards, is a recharacterization of unidirectional, bidirectional, as well as the addition of dynamic flows. And I think Michael handled this well already. You start messing around with things, you can make lots of flows in a building. It's possible, and firefighters can mess things up, okay? But essentially, the vent profiles that I want to make sure that firefighters in the room understand at 2 o'clock in the morning when they look up at 20 stories up and go, oh, I got a fire on the 20th floor. Understand what that vent profile is telling you, okay? Because there's a lot of information, and if you understand the non-standard or atypical conditions, you won't put yourself on the wrong side of the shotgun. And that's what we saw in the fire test. There was a fire called Vandalia in New York, and that fire in Vandalia killed 3 firefighters. It was a blowtorch down the hallway. And I'll tell you what happened. We had a monster fan on one side of the building and a monster fan at a doorway. And we were going to see if we could create a fire that moved really fast And could we restrain it with a fan equally? Well, that was like day 5 or 4 of experiments. And we used a very important, a UL rated coat hanger around the door, connected to the wall, and 4 days of being shook by a fan. You know what happens to a coat hanger after you go back and forth like that? The door slammed. So essentially the experiment reversed. We had a unidirectional flow. It burnt the hallway out in this high rise in Chicago, and that high rise looked exactly like Vandalia. And the heat and if you will, modeling the FDS modeling, you could have put them side by side for Vandalia. So that's kind of the energy that was transferred. So we really wanted people to understand what to see and what to look for. So I created these, if you will, nomenclature for the pictures I had taken, because I started seeing, again, I'm looking at from my role at the time, which was operational safety, to evaluate for hostile fire, structural failure, and firefighter physiological, kinesiological, and psychological effects. So this became, sort of a little passion. And I noted some stuff. And so when unidirectional flow, a flow of smoke or air moving in a single direction, right? Or air, right? So if it's like that, you know that right away, there's got to be an inlet, there's got to be an outlet. There is something that's not a normal flow. It's atypical, right? Because normally smoke, top, air, bottom, bidirectional, right? Bidirectional, right? Pretty straightforward. Dynamic is a unidirectional or bidirectional flow of smoke or air that presents irregular stratification, okay? And a shape that alternates in direction, such as pulsations. So when we look at that, eccentric, it's pretty obvious. That's not normal. Air is acting on the opening, right? And you can see, we built a couple of graphics. It doesn't have to be a closed box. There could be an open door there, right? This room could be so full of smoke and fire, and the wind's blowing that way, and we're getting that eccentric profile, but that door could be open, the air that's blowing down there. Or it could be a closed box, okay? And projected. So again, this projection is when we failed the door. And that whole instrument row on the 3rd floor disappeared. Lots of money was cameras and everything just kind of burned up. But again, the door, it shows it, 2 models, if you will. It doesn't have to be open, okay? It depends on how the air enters into the opening. Now, this is inverted projected. Okay, so I don't have a pure inverted, but the fact is that the fire or smoke is coming off the bottom of cell, okay? And it just happens to be projected as well, right? And you can see from this little graphic how that's possible, right? Where the air enters the opening. Conceptually, what you have to think about there is a really tall building here and a less tall building here. And the wind could be blowing this way, and it could be pushing air that way, and basically go in the top of the window, as one example, okay? And here's one that is inverted, eccentric, and projected. Not normal, right? Atypical. Hollowed. So when it's just, the flames are just hanging at the opening, you might see a little flame, or you might not see any flame at the opening, just a glow inside. That's an inlet, right? And then puffing as part of the dynamic flow. So Governor's Island typically has lots of wind when the experiments were planned to be run. I believe it was October. We had no wind. We had to use fans. The last day of the experiments, the wind came up. The wind produced effects that were far more deadly than a directed fan. like much more violent, okay? And what you're seeing there is that mixing the combustion cycle, air being pushed in at the eccentric, pushed in, being consumed, fire grows, pushes back out, no air back there, collapses, in it comes again. So that's the combustion cycle. Right? So Puff the Magic Dragon, if you will. And this was another one where we used the fan. This is where we had the door fail on the other side. So this one's referred to as starfire. So you can see as the air is pumped in. Now appreciate that we've opened the door on the other side, right? That fire is blowing up stairwells as well. But you see it comes out and it lays flat against the building, or some degree of. So it looks like a big star. Okay. There you go. Okay. Pretty mean fire. Right? And so there's actual videos of fires in France and stuff like that. You see some of these characteristics. You may not see them all the time. But the key is to understand why this is and how this works. You can see in that upper right for you, if the building had continued further up, you would have a bit of a hollow and you start to see some of that starfire. So again, hollow and starfire can be very much related, and that's related to this. We regularly speak to the issue in the fire service of fuel geometry, building geometry, but we never really talk about the geometry of the air interacting with the fuel. Unless, of course, you're into fast cars with, modern day engines. The whole idea of combustion efficiency comes into play. Essentially, what we have to understand is what is the angle of air striking the fuel? And that's essentially what's happening there, is they change the angle, you get a better mix, less air, and that's what happens in wind-driven fires. We get a better mixture in that fuel, and you have accelerated temperatures, you have convective heat, and it turns into a blowtorch. Burn a door right off a building, into the hallway. Anybody in that hallway. Brent talks about, if you will, the idea of door control. Critical in wind-impacted fires. So understanding and observing the difference, you can see that's an inlet. Well, that's an eccentric profile, vent profile, and I have over here a full, if you will, projected, all fire, not normal. Okay, so that should tell you that wind is impacting that. So that takes me into another part of the fire dynamics program, and we modeled on Catherine Lamb's effective command. We took some of that modeling and in terms of the action steps of that model, we built tactical bricks. And this again was introduced to NFPA 1700. Everything you could do with water and everything you could do with air to fight a fire has been characterized in the tactical bricks. There are no other tactics. This is it, right? This is the whole grommet. But the intent was to describe these extinguishing media as it relates to air and water. So what we did was we described, if you will, what does the commander want with the tactical objective? How does it work? What are the fire dynamics principles of that action? Considerations for the company officer. Hey, what does the science tell us? What is UL? What is NRC? What is MSB? All the science agencies tell us the way or how we should do stuff. Task level, as well as Plan B, and we talked a lot about Plan B yesterday, right? And safety considerations, keeping out of trouble. So we broke down all the stuff associated with, like, we call Michael's curtain non-ventilation, and we have that described using this format, again in NFPA 1700. Okay. Now, exterior control, some refer to it as transitional attack. We in Ottawa refer to it as exterior control. Transitional attack was, I think, a way to get around the idea of being defensive on the fire ground as opposed to being aggressively offensive. So it's just how you put the water in, right? And I'm going to give you a quick example of how this is written up. The whole tactical objective associated with exterior application of water is to improve tenability for and interior conditions for fire attack. And then how it works, that is associated with fire science. I won't read it, you can. And I think Brent really gave you a good understanding today, hitting the ceiling or hitting the doorway, how you can utilize large water to achieve your objective, right? To get the water in the right place. So, example, of exterior control, using elevating devices. And this was a wind-driven fire we had in downtown Ottawa about a year and a half, 2 years ago. Master streams, aerial devices, and then hooking up in a dry riser because it was under construction and putting it out on the 21st and floors above, utilizing hand lights. So, and that's the building today. I took a picture the other day. Very nice, right? Fire control using adjoining balconies, right? And in my high-rise procedures, when I came on the department, because our high-rise procedures were informed by a coroner's jury as well as the National Research Council, they told us to seek refuge on the same side as the fire, okay? And that's related to the pressures being the same. Flanking the fire, and when we talk about flanking the fire, coming up through a stairwell, going into another apartment, breaking through walls if you have to, and get to that fire compartment, or from below, bring a line up from below, another floor, get into that other compartment, put your water in there. Brent took this fire control using a cellar nozzle. He demonstrated that. We developed that technique in about 2008 in Ottawa, and then post-Wellesley, I went to Toronto, and I'm proud to say Toronto was the first fire department in the world to put out a fire using a Bresnan rotary that I know of, exterior using the Bresnan rotary technique that we developed in Ottawa. So, and it's very effective. The amount of water that is associated with that flow. I'm about 20 feet away from that opening, and I am soaked, right? That's just the Bresnan running outside, what I mean? So we saw the curtain, the KO curtain. That takes a lot of staff to do that. We have also, if you will, the floor below. Brent went through that. And I guess the important thing here in sort of concluding is we did that work in Governor's Island in 2008. Okay? In 2014, 2 firefighters in Boston were killed in the Back Bay. Yeah, not a high rise. But you can see the conditions, and I don't believe they understood what they had in terms of the behaviors, right? So you could see that dynamic flow. And understanding that dynamic flow, unfortunately, 2 Boston firefighters died in that fire. And firefighters are still dying because of wind-driven fires. And it's because they don't know those 6 basic forms to look for and understand the controls, right? And that is critical. And a lot of that, and most of that information is out there. And Brent's done a phenomenal job bringing it into a very successful high-rise program. So, in conclusion, that ventilation profile, what you see is critical, and there's a whole bunch of factors associated with it. It's a continuous assessment, right? Until you fully resolve the risk, and remember to evaluate that ventilation profile and be safe. And if I conclude with these 2 Ottawa firefighters, one is holding a lamp and the other is holding a tool. It's the lamp of knowledge and good practice. And this, symposium has demonstrated the need for making sure the knowledge and the practice get together, right? Thank you very much. Anybody would like that? Firedynamicstraining.ca. You can get all these presentations. There's tons of written material there. It's being updated probably in another month. So, thank you.